Our next speaker is Andreas, and he'll be talking about accuracy of adaptive discontinuous Galerkin simulations.
Thank you very much. This work concerning the accuracy of discontinuous Galerkin methods comes from a cooperation between the Naval Postgraduate School in California with Frank Giraldo and me, Jörn Behrens from Hamburg, and Volkmar Wirth from Mainz. After a very short motivation, I will show you some details of the numerical model that we are using with the discontinuous Galerkin method, the IMAX method for time integration, and some verification results. This verification considers the accuracy of the discontinuous Galerkin method. So for the third section, I still have to show somehow how accurate is the adaptive simulation. And I want to do this by comparing the adaptive simulation of a warm air bubble with a uniform simulation. For the motivation, I show you a warm air bubble simulation. The color shows the deviation of the potential temperature from the background state, and the black lines show the locally refined triangular grid. Inside of the warm air bubble, a resolution of 3 meters is used. I start the movie, the bubble rises, and you can see the mesh is continuously adapted at the position of the warm air bubble. If I want to compute the same result with a uniform mesh, I would have to use this resolution of 3 meters everywhere. As an illustration, I show you here the initial condition with a uniform mesh of 3 meters, the left half here on the right-hand side. When considering these two initial conditions, the question comes to my mind, do they produce the same accuracy? Probably not exactly, because in the adaptive simulation, we use a fairly coarse resolution in the environment. But we could make the refinement region larger. So the question is, where can the spatial resolution be coarsened without losing accuracy? I will come to these questions in the third section. Before I want to explain the numerical model. We consider the compressible Euler equations with artificial viscosity given by these 3 equations here. The prognostic variables are density rho, velocity field u, and potential temperature given by this equation with the temperature T and pressure P given by the equation of state. As boundary conditions, we use solid wall boundary conditions because those are the boundary conditions that are used in the bubble test cases that we are considering in this work. For the spatial discretization, we use a discontinuous Galerkin method that was introduced by Giraldo and Warburton in 2008. It was introduced for shallow water equations. For explaining the main idea, I show you I write the Euler equation in this form with a flux tensor f and a source function s. Then I multiply this function with a test function psi and integrate over one element of our mesh. With the integration by parts, I bring this derivative in front of the flux tensor, in front of the test function. I get this boundary integral. I replace the flux with a so-called numerical flux f star and bring the derivative again back. That's the so-called strong formulation. Then we use an expansion by basis functions, by polynomial basis functions, and after a few steps of calculation, we get this equation here for the time derivative of our unknowns. And these functions psi hat, they are the product of the inverse mass matrix with the basis functions. For the numerical fluxes, we use Ruzanov flux, and for the viscosity terms, we use a so-called local DG approach. By using suitable quadrature rules, the right-hand side of this equation 7 is known. The task remains to integrate this equation in time. And for this purpose, we use an IMAX method that was introduced by Rastelli and Giraldo in 2009. Again, I start with this form of the equations. Now I introduce a linear term LQ, which describes sound waves and gravity waves, which we don't want to resolve explicitly, and therefore we solve them implicitly. We do this by using a backwalk difference of order 2 in this work. Here you can see the details, and I don't want to explain all the details. The main idea is to solve an explicit predictor first, and then solve the system with a GMRES iteration. For the adaptive mesh refinement, we use a conforming triangular mesh. Adaptive mesh refinement is done with a function library called Amatos, which was developed by Jan Behrens and which uses a space-filling curve approach. Here, the sketch shows an example of such a space-filling curve. For the refinement criterion, we use a very simple criterion in this work here. Of course, it does not work in more realistic applications, but for the simple bubble test cases, it works quite well. We use a finest resolution wherever the deviation of the potential temperature from the background state is larger or equal to the maximum of the potential temperature divided by 10. In addition, we add 2 or 3 fine elements for avoiding that the bubble moves into the coarse resolution. I come back to the question if this refinement region is large enough in the third section. For the verification, I show you first a spatial convergence study with the method of manufactured solutions. Here you can see the L2 error as a function of rho times theta, as a function of the shortest element edge, delta x, of our mesh, for different polynomial orders of 3, 4, 6, and 9. The black points show the experimental result, and the red lines show the theoretical expected optimal order of conversions. And you can see here in this case, it works very well. I tested up to 10th order, and yes, there I stopped. But the results that I show here in this presentation are always calculated with 3rd order because, in our opinion, that was a good compromise. As an example for a test case, I show you a density current test case of Straka et al. From 1993. It is initialized by a cold air bubble in a much larger domain than before, and the amplitude of this cold air bubble is minus 15 Kelvin in temperature. I started the movie, and you can see the bubble falls down and flows along the lower boundary, and finally some Kelvin-Helmholtz rotors occur. Straka et al. Compare in their publication different simulations by using this fairly high-resolved simulation. I have to say, I did not plot the mesh inside of the density current. Inside the density current, there is always used the finest resolution of this mesh. And Straka et al., they compared different simulations at a much coarser resolution by using this high-resolution result as reference. And for this purpose, I show you also our coarse resolution result. We use here 226 meters, and I start the movie, and you can see it is of course not as good as before. But for this very coarse resolution with 3rd order polynomials in each triangle, I think this result is still quite nice. Straka et al. Compare different values, like for example the amplitude of the density current at this time, t 900 seconds, and the front position at this time. I made a small histogram of the values from Straka et al. That you can see here for the front position. The bars show the number of simulations from Straka et al. That produce values between these values here on the horizontal axis. And the blue arrows show our low resolution results for 2 different setups for our limiter. And the red arrows show our and Straka's reference simulation. The same for the amplitude is shown here on the right-hand side. And you can see the spread in the results of Straka it's much larger, and our coarse resolution results are very nicely, very, very close to the reference simulations. So much for the verification. Now I come to the accuracy of adaptive compared to uniform simulations, and to the questions, do they produce the same accuracy, and where can the spatial resolution be coarsened without losing accuracy? This is my first question. In practice, they don't have to produce exactly the same accuracy. So the second question is, where can the spatial resolution be coarsened without losing accuracy significantly? And these two questions assume that the finest resolution is somehow given by some finest scales that we want to resolve. But in many applications in meteorology, the finest scales can't be resolved. And so in meteorology, often the question is much more important. Given a certain amount of CPU time, is an adaptive simulation more accurate than a uniform simulation? These are three questions, and now I will show you the answers that we found for the warm air bubble test case with a constant viscosity of 0.1 square meter per second. For the first question, I took the adaptive simulation, subtract the result of the uniform simulation, and computed the absolute value and got this result here. For making it easier to see, I make it larger. So now you can see the details. The color map is logarithmic. So the values here are still in the order of 10 to the minus 4 Kelvin. The fact that the largest difference is surrounding the finest resolution is simply produced by a too small refinement region. The bubble was not completely covered by the finest resolution, and for this reason, the largest difference is next to the finest resolution. So this result is not surprising. Now I compute the L2 norm of this result and plot it into a figure here as a function of the average number of elements until the time t, 200 seconds, that I considered here in this case. I did this not only for this very small refinement region, I extended the refinement region more and more and got this curve here. As you can see here at this early time, 200 seconds, you can still distinguish between those simulations that were significantly affected because the refinement region did not cover the whole warm air bubble, and others where the L2 norm of the difference is approximately constant. I think these oscillations here come from coarse elements in the edges of the domain. At later times, it becomes more and more difficult to distinguish between those simulations that were significantly affected and those that were not. And I think at this stage here, 600 seconds, it is almost impossible to distinguish, because somehow each simulation seems somehow to be affected by using adaptive mesh refinement. I think this result is reasonable because the rising warm air bubble produces a circulation in the whole domain that is simulated on a fairly coarse mesh in the adaptive computation. However, I did not expect that this curve is so continuously decreasing. I expected that at some point there should appear some kind of jumps, helping us to decide how large the refinement region should be. At later times, there are some kind of jumps, but they vanish fairly soon again. So I think this result demonstrates in the warm air bubble test case, adaptive simulations produce never exactly the same result as uniform simulations. That's the result for the first question. For the second question, we needed some kind of error indicator. I don't have time to explain you in all the detail how we defined the error indicator. Mainly, we consider perturbations in the shape of the warm air bubble. If you are interested in learning more about it, please ask me later. I just show you now some results using our error indicator that we defined. We used our error indicator for defining a relative error of additional error of using adaptive mesh refinement. And it is plotted here as a function of the number of elements of the adaptive simulation divided by the number of elements of the uniform simulation for 3 different resolutions, 4, 3, and 2 meters. As an example, I take the result for 3 meter finest resolution, and you can see, according to this error indicator, the additional error by using adaptive mesh refinement is smaller than 1% if the adaptive simulation uses more than 50% of the number of elements of the uniform 3 meter resolution simulation. For showing you how it looks like, here you can see this fairly large refinement region, and according to this error indicator, the additional error is smaller than 1% of the numerical error of the right of the uniform simulation shown on the right hand side. So we come to the conclusion here that for this warm air bubble test case, the additional error by adaptivity is smaller than 1% of the total numerical error if more than about 50% of the number of elements of a uniform simulation are used. That's our result for the second question. For considering the question, how does this compare when the CPU time is given, I show you this error indicator for 3 different resolutions as a function of the average number of elements. For making it easier to see, I marked the uniform results with the red circle and the adaptive results that use on average the same number of elements with the black circle. And here you can see, according to this error indicator, the adaptive simulation error is actually more accurate than the uniform simulation. Depending on the overhead of the adaptive mesh refinement, we have to reduce the number of elements in the adaptive computations for really getting the same amount of CPU time. So if you consider this more in detail, you get the result. The adaptive simulation of the warm air bubble test case is more accurate if more than about 40% of the number of elements of a high-resolution uniform simulation are used. So that's our result for the third question. Until now, these results are all obtained for the warm air bubble test case. So the next step is now to consider different applications, like, for example, larger domains, 3D, and moisture. Thank you for your attention.
Yes.
Just maybe philosophical, but my answer to the question, or my approach to this question would be that in an adaptive you would usually go finer. I mean, you sort of limited how fine you go. And in a real comparison, you'd say, if I take the same amount of degrees of freedom, which one wins? No?
The last question was this question,
yeah.
Which one wins when I give the number of degrees of freedom. I started with the other questions because I thought, well, if the fine resolution is somehow given, if I want to reach a certain scale in my simulation, then how do they compare?
It's just the test case you chose is particularly, I mean, where these little whirls come out, then the adaptive would do much better eventually when it gets really complicated. Because you can go really fine in those regions, whereas the fixed scale uniform one can't do anything there.
Yes.
I mean, okay, I mean that needs
maybe we should try.
Yeah. Any other questions? Okay.
Do you think your convergence results might be sensitive to your choice of refinement criteria?
The convergence study was without adaptive mesh refinement.
So you had some plots of the errors coming down as you allowed a greater number of average elements.
Okay. On some of the last slides, it is definitely, it is probably sensitive to the shape of the refinement region, and we have not tested to change this shape. But well, maybe one can try. Maybe one can get better results by using a different shape. But as these results seem to indicate that a fairly large refinement region might be useful, I don't think that there is much to get out of a different shape because it is already very, very big.
Any questions? Okay, I have one question. Can you explain the adaptivity criteria you used?
That's simply where the potential temperature increases a certain value, given finest resolution is used. So it's very, very simple. And I don't think that it is useful in any realistic application. But for these bubble test cases, it works.
Okay, thank you very much. It is time.